Hello.
John Schipp is the HackerCon 1 Captain Flag /That Top winner. He's a black badge holder and has spoken at every HackerCon since then. Is that correct?
That is correct.
So please join me in welcoming John Schipp. Thank you.
Hello, everyone. All right. Okay, so today I'm here. My goal is to persuade everybody to try out the netsniff NG toolkit. And we're going to go through a bunch of examples, and this will be primarily a technical talk, so bear with me. So the first question is, why would we want to use netsniff NG? Netsniff NG is a suite of tools. There's a number of them. There's 8. And there are 7 of them that are pretty much production ready. It's a fairly new toolkit, and it's coming to a good stage in development. Now, the word up here that's interesting is high performance. And we'll talk about that, why netsniff NG could be called a high performance suite of tools. So let's get started here. First, a little bit about me, some introductory things. I just took a new job recently at the National Center for Supercomputing Applications, which I like very much. And you may have heard of them if you're familiar with Bro. Is anybody familiar with the Bro project? All right, so we have involvement in the Bro project. Some of our developers on the team. I'm the founder of the Du Bois County Linux User Group, the Southern Indiana Computer Club, and I am a contributor to netsniff NG. Mainly documentation, but I submitted some patches for code, and I do testing and reviewing. Okay, so a little bit about netsniff NG. So it started in 2009. Like most open source projects, it was done in the free time of a few people. So there's 2 core or main developers now, maintainers, and that is Tobias Klauser and Daniel Borkman. And they are both Linux kernel developers. So netsniff NG is packaged in a number of Linux distributions. So you can find a package manager and usually have it. It'll probably be an older version though. There'll be new packages coming out in the future. So what can we use it for? Well, standard network tools are used for analysis and debugging, monitoring, and auditing. And netsniff NG can fulfill all those gaps. So here's an overview of the toolkit. And you can see there's quite a few tools. We'll only talk about a few of them today. Primarily IFPPS, BPFC, netsniff NG, and TraffGen with a little bit of FlowTop in the mix. So let's put this into the bigger picture. What does this look like? So at the top we see the toolkit, and the branches are the domains of each tool. So we have traffic encryption, measurement, generation, and capturing. So you can see where that fits in. So the gain. So netsniff NG and TraffGen use memory-mapped I/O buffers to buffer and then process packets. And that is about the fastest you can get on a Linux system from user space. So the buffers are memory mapped between kernel space and user space. So there's less amount of interrupt switch between the two and less context switches. And we use, in Linux, our Linux system, we use the system call socket, and we pass specific options to use PF packets to get full access to all parts of the packet, from the headers to the payload. And at the bottom, you can see where it mentions that gives us control over the entire packet, including the data link layer. And like, for example, HPing uses raw sockets, and you don't get the data link layer in that. It's IP and above whenever you're generating traffic. However, with TraffGen, we can get the whole thing. It is optimized for Linux. Because of our developers, or the core developers, are kernel developers, and they work in network development and a few other areas. They are familiar with the internals, and thus they can take that with their knowledge and then move that into netsniff NG to take advantage of new features, which we'll talk about. It's also a very small code footprint. Tools are very small in size. So, as mentioned, it is a good point in its life cycle. So there's been a lot of new additions over the past year, and the tools are relatively stable now and production ready. And I've used them in production for a company already to do full content packet capture with netsniff NG, and I've used TraffGen in performance tests, and we'll get into that. So let's see here. So another reason you could that's netsniff NG can be useful if you're a developer. As I mentioned, that they're kernel developers, so they have some of the latest additions integrated to netsniff-ng, and if you want to review examples of source code using the latest developments from the kernel, you can review the code. Because maybe there's not many other tools that use a particular feature available in the kernel. So here's some latest developments in the Linux kernel. Available in 3.2 and above is tpacket v3. So before we were using tpacket v2, and this is just a structure to store packets in, and libpcap uses tpacket v2, so thus all the tools that are using the libpcap library will also then use tpacket version 2. Now netsniff-ng is not reliant on libpcap for packet processing. So they actually have the tpacket v3 code in there. So on the discussion mailing list, on one of the Linux kernel mailing lists, tpacket v3 was suggested to have a 15 to 20% reduction in CPU usage and a 20% increase in packet capture processing rate. So that is something to consider in high-performance applications if you can use an application that can take the value from this new tpacket v3 structure. Another thing that was recent in the Linux kernel, 3.10, so that's a few months ago probably, is a new BPF instruction. So this is really nice. So with this instruction, what we can do is you can actually just write packet headers to disk, truncating the payload. And all you have to do, I have an example of the instruction at the bottom. So in high-level BPF language, you would say load POFF, that is the instruction. And then we want to return the value that's in the accumulator, the ret A. That will then return, once you implement that into the socket, so you tell netsniff-ng to read that filter file, header.ppfc in my example, and then the packets will be written to disk, headers only, data truncated. Because before, that would kind of suck. You'd probably have to do some sort of math, because we have the UDP 8-byte header, the TCP 20-byte header, and you have to work in all that. So this is really nice. This is a new addition. And this is not implemented in libpcap. That is not to say that it won't be in the future. But this is a new instruction, and it is in BPFC, which is a part of the netsniff-ng suite. Here's another example of a neat little addition, and this is the virtual netleak monitoring device. So you can create a new pseudo interface, and it can actually record netlink messages, which are basically networking-related messages passed between the kernel and user space for inter-process communication type things. And this is actually a packet analyzer neutral, so you can do this with netsniff-ng, and you could also do this with TCP dump or any other tool. Okay, so now let's get into netsniff-ng. So it is a analyzer, replayer, and packet recorder. And it is now included in, well, first I should ask, is anybody familiar with Security Onion? Any hands in the air? Security Onion? So yeah, most of us are familiar with Security Onion. It's a very cool project. netsniff-ng is the backbone for packet capture recording in Security Onion now. It replaced Daemon Longer maybe a year ago. I don't remember what the time frame was for that. And I've submitted a few patches to Security Onion to actually allow you to view the PCAP stats from netsniff-ng whenever you use the SOStat tool. And then now I submit also a patch to do in the menu. When you're setting up, you can actually specify the ring buffer size, the size of the ring buffer in memory that you can allocate packets. So you can increase the size if you need to, if you have a lot of packets coming in. netsniff-ng enables the BPF JIT compiler. So the JIT compiler, just in time, is a compiler in the kernel where whenever what actually happens is the difference between a BPF compiler regularly and the JIT is that JIT converted into native architecture code. So it tends to be quicker because you're running on native instructions. So we'll put a JIT image in there, and then it'll compile the stuff, and then it'll be native code. So in Linux kernels, I'm not sure what version, that's been in there for a while though, the JIT, but netsniff-ng will set a value in your syscontrol settings to enable the JIT and take advantage of that. And the result is you get about 50 nanoseconds of performance increase per packet coming in where the BPF filter has to be applied to the packet. And it also does basic OS tuning. So in your procnet, or not procnet, there's certain system settings like your RM and WM buffers. It increases those sizes to large values so you can buffer more traffic. So. And with the top part, we're at now speeds comparable to PF ring in transparent mode 0. So one neat thing is that the Linux kernel, if you don't want to use BPF, it has a few options for packet types. So instead of actually applying a BPF filter, there's socket options where you can say, I only want broadcast traffic, multicast traffic that are not, the socket says, oh, we'll only capture these, and this is actually not done in BPF. And netsniff NG has the option to take advantage of that. So what you do is, you just say, hey, there's a few options that we support, actually support all the packet types, and you say -- host if you want all traffic that is addressed to the host that you're on. -- broadcast. It automatically get all the broadcast traffic it sees, it writes it. So you don't actually have to do a BPF filter for broadcast, which is pretty cool. So here's a few examples. So netsniff NG is pretty intuitive. The options are very easy to read in, out. So I really like that. Makes it simple. So things are coming in, things are going out. In can be a file. Interface, you can replay to another interface. So you say in interface, out interface. You can do things like that. And output to a directory, output to a single file. So here we give an example. We're doing a full content, how we may do a full daily content packet capturing scenario. We want to use -- silent so it doesn't print to the terminal, because if you print to the terminal, you're going to have interrupts, and then it'll take more processing time. For every packet, the terminal needs to be interrupted to print to the screen. And then we specify a ring buffer size. We set the priority to high, which is pretty much the same as setting the nice level to -20, so on and so forth. And we want to rotate at 24 hours. So every time we hit 24 hours, a new PCAP file will be rewritten. And we can also do this from wireless. We can sniff from wireless, raw, 802.11, replay from interface to interface, and we can also apply a BPF filter. This is another example where you just say, you can actually use TCP dump like filters, so libpcap filters, where TCP and port 22. And what it actually does, so netsniff NG does not rely on, as I mentioned, to use libpcap for packet processing, but it does use it to allow people to make easy filters without using a Slimler-like code to write their filters, which is kind of a pain. So it is compiled with the libpcap library, but that is only to compile the filters. Or you can specify filters with BPF-C and then integrate those in there by specifying the file. So here's a little output. This might not be too visible from where you guys are sitting. We can, if you use the -- verbose option, we get the default ring buffer size, the number of frames that can fit in the buffer, the max frame size, and so on and so forth. netsniff NG gives you does a MAC OUI lookup, so you get the vendor of your MAC address, like Wireshark and many other tools. GeoIP locations built in, which is kind of nice. So in the example below, you see that we have a packet that is sent to Sydney, Australia. Yes, Bill. Yes, there is. I think it's -D though. Yeah. Yeah, there's also, so I'm giving you guys the GNU long format options. There are also the short options too, but just for readability. Yeah, for readability, it's easier to use the long format because it has a little description of what it is. Yeah, no problem. And then we got some statistics that come with most packet capturing tools, and that is incoming packets, the number that were processed, those that passed the filter, those that dropped, and the percentage of the drop rate in a %, and then the capture duration. So let's move on to the next tool. This is TrafGen. So TrafGen is a traffic generator. This is really cool. This can be used for fuzzing, and it can also be used for just generating packets. You want to see certain responses from machines, or performance metrics, which is, I think, is a key hit for this tool. It is multi-threaded, and it is a low-level traffic generator. As we talked about before, with the socket it uses, we could have the entire access to the frame. So here is an example of this graph here shows TrafGen versus Malzahn, or Malzahn, or versus PacketGen. PacketGen is the Linux kernel packet generator. And this is a kernel module that is used among the kernel developers and other people to stress test machines and stacks. And this is a performance metric against that, and we can see that TrafGen is very, very close to PacketGen. This was done from Daniel's thesis, one of our core developers. PacketGen is quite a little bit faster in his performance tests. Look at the frame sizes, at the bottom. But TrafGen is up there with them. So, which is really cool, because this is done from user space, whereas the PacketGen utility is actually done in a kernel module, so it's done completely in the kernel. So a little comparison between the two. PacketGen is faster on smaller packet sizes. It's about the same otherwise between TraftGen and PacketGen. So I'll give an example of small packet size, 64 bytes. TraftGen was able to do, on the system I was using, 520,000 packets per second. And with PacketGen, I was able to increase that to about 620,000 packets per second. TraftGen is more customizable. This is because of the way that PacketGen is designed, which I think I have an example next slide. You actually use the proc file system. You actually echo values into procfs. And there are certain values that you can echo, and then pretty much you don't have any other choices. With PacketGen, we can create a file, a configuration file of bytes, and from the beginning of the frame to wherever you want to stop, send it out. So you have complete control, and we'll give an example of that coming up shortly. And as I mentioned, TraftGen or PacketGen uses the procfs, but TraftGen, besides being able to read from a configuration file, it also has expressions, built-in macros, so you can do things quicker. This is an example of PacketGen. So basically, you echo a bunch of values to procfs, and then when you're done with all this, so this basically says, I want to create a packet with the source MAC address, the destination MAC address, a destination IP address, source ports, and at the very end, we'll run another command to tell the kernel module to send that data and read from those values. And it sends it out. Here's TraftGen. So this is in hexadecimal. But it doesn't have to be like this. There are ways to do this. Well, this is nice to have hexadecimal values, because you can just copy and paste from Wireshark's protocol dissectors, right? And paste it in here, and you can make your own stuff like that. But we can actually use decimal, ASCII, and so on. So we have a lot of control. Okay, so here's some performance metrics, or a basic performance metric I did. This is on an old machine, and it is reported. I will preface this with that many people are reporting line rate among the frame sizes for TraftGen for 1 gigabits per second Ethernet. My machine, being 6 to 7 years old, wasn't able to quite make that. But you can see in the 1 gigabit line rate attempts for the 64 byte packets, I got 24%, and as the packet size increases, I get closer to line rate. So we see 96%, 97, 98%, and then 98%. So that's pretty much line rate, very close, 2% off for those last two sizes. 10 gigabits per second, a little harder to do. Again, I'm using a older machine. This is the same machine that had another slot with a few network cards. And I did a comparison with TraftGen and PacketGen, and basically for PacketGen, it was about double on the smaller frame sizes. So where I have 3%, they would have 6% in PacketGen in performance. So this is a basic test. I'll do more later with actual multiple runs and such, and release those. But that gives you an example. So here's how we can use TraftGen. If you want to send 15 million packets out of an interface using all the cores available on your system, you would run this command. You just say, hey, I want to read in this configuration file. I call it 64.cfg, which is telling that it is 64 bytes, a packet of 64 bytes. Output it to E2 and specify the value of the number of packets to regenerate. So here we can do a fuzzing test. So if you have this fuzz, this configuration file with a bunch of random data, and you want to fuzz a network stack, you can put it in there, and you can use a smoke test option. There's also some seed values where, so basically this will run this, and then it will do an ICMP echo request to the destination machine and see if it's still alive. Then it'll generate a seed value if you specify that option for debugging. So you can find out if it crashed. It can generate raw 802.11 frames. So open a Mon0 interface, right? Get raw access to the device, and then we can generate traffic out like that. And in this example, I also specified we only want to use 2 CPUs. And another thing about TraftGen is that we can use STD in, STD out. So there's a built-in configuration. -E, we pipe it out to another instance of TraftGen, tell it to read it in, and then pass it along to the interface. So here's the expression language. This is nice. So, but we have a few macros. We have fill, random, dynamic random, constants, decrementers, and incrementers. A few examples. Let's go to the next slide. So for fill, number 2. So we say we want to fill some data for n bytes. So we want to say if we want to do fill a packet of 0xFF, the 255 in decimal, 10 times. So we make a 10 byte packet of those values. We can just do fill put in those two parameters for the almost like function thing, the macro, and then we can send it out. So you can do cool things like that. So if you want to do a random packet, we can look at this instance. So if you want to generate a packet of 582 bytes, completely random, you can do that. And each time, it'll be a random packet generated. So here's the types. So I mentioned that we can do hexadecimal, as you saw previously, and we can do ASCII, characters, strings, that would be the ASCII, and binary. So we can go actually down to the bit levels and do binary, which is really cool. So, and we can also do shellcode. So if any people are interested in setting shellcode, you can do that. We just escape it out. So the C preprocessor. So we can actually, TrackGen integrates with the C preprocessor, so we can use definitions and things that the C preprocessor can read and replace in the TrackGen configuration file. And it actually includes a file, stddef.h, which is a header file full of already pre-made options and headers to make it easier for you. So for example, if you want to say in the Ethernet frame, you want to say, hey, we have the destination MAC, source MAC, and then the protocol field, which says what is going to be above. What is going to be above this frame? And that is going to be IP in most cases, right? So there's an option if you don't know what the number is off the top of your head. You can just tell TrackGen to put in ETH_P_IP, and that puts the value that means, hey, there's going to be IP, and that is 0800 in hex. So this is how we create packets. So basically, if you have a curly brace, left curly brace, packet data, right curly brace, right? And the packet data goes in between, and for each curly brace, that is a packet. If you have a file and you want to do curly brace, packet data, curly brace, enter, new line, left curly brace, packet data, right curly brace, that's two packets. So between each set of curly braces is a single packet. So you can make multiple packets in a single file. Okay, so again, the random data examples on the fill. And if you have a good with the scripting language, you can use Python. You can just generate some data. Like here, Python, we use string concatenation and math on using strings, and Python basically just multiplies a string times 8 and it prints it 8 times. So we can do that and make a packet. And here's the example. The result of that little Python script is this. I removed 6 lines of the packet because I multiplied by 8 and I want to fill the screen. And then here's the result. So I generated it out with TrackGen. I run netsniff ng. It printed to the screen. You can see my packet, my packet, my packet under the ASCII decoder. And if you want to know why it's cut off at the ET in the beginning of the character, is because my packet is actually is now the values written in the Ethernet fields. And of course, that's not decoded. So if you do a hex dump on that, you'll find out that 04 is M, and so on and so forth. Just kind of nice. So here's a little more advanced example. This is a UDP configuration. So we're going to use dynamic elements, those macros, and we say, from a configuration file, we can specify the number of CPUs we want to use. I think that's pretty cool. So what we do is we say, use CPU 0 through 3, so 4 CPUs, randomize the Ethernet link layer, IP version protocol. We want to do a 20-byte random IP header. It's going to be invalid, most likely. So this is going to be stuff. And then randomize the UDP header, and then randomize 1,472 bytes of payload data. And we send that out, and it'll do it. Here's a more complex configuration. This is using the built-in TrackGen-E. If you use this, it's a built-in TCP configuration that you can use and modify. So we fill the MAC address, destination MAC address, with the values as ETH and A length, which is 6. It's just a macro, or not a macro, it is a definition in the C preprocessor from that file that says this is going to be 6. So the length of a MAC address is 6 bytes, as most of us know. So put that in there, 6. And then we say we want these 3 bytes of the source MAC. We're going to randomize the last 3 bytes, and so on and so forth. We specify in binary the IP4 version, international header length, and type of service, so on and so forth. And we do the TTL type, time to live, TCP protocol, hex value 06, the checksum, get a macro for checksums, and so on and so forth. So we get pretty granular, actually very granular, just about as granular as you can get. And then we do some bit shifting for the TCP header. So that's pretty cool. At the end, we put an ASCII string in that says gotcha, and that is the packet. All right, so we can actually take an existing, if you don't want to write your own stuff, I understand, because it's difficult. It takes time. You can take an existing PCAP, say you use TCP dump or whatever tool you like to use. You can actually tell netsniff ng to pipe it to std out, and what netsniff ng does, it puts it in a TrackGen element. It puts them in the element format, so hex values. You can then take that value, pipe it then, into trafgen using stdin. So you say --n space in, which is the common notation for reading from standard in. And then we want to generate 1 million packets from that piquet file. Here's a script I wrote to make it a little bit easier for some trafgen configuration. So I wrote a script called genconfig. This is in bash. And what it does is it has some pre-made configurations. I'm going to add more as I have time. I currently have UDP syslog messages, so you can do a syslog message. It's predefined. The value you can modify, but if you want to increase the actual message length, like it says something like trafgen stress tester. If you want to increase that, you'd also have to increase the values for the number of bytes in the IP, so it's the header, so it's valid. But it can be done real simply. And then the RFC 2544 article is a document that specifies it's a performance metric document that it is the benchmark methodology for testing network devices. And the frame size in section, I think it's 9.2 or 9.4, is the set that you should use if you're testing Ethernet devices. If you want to do performance metric, you should use these frame sizes, basically what it says. I wrote each configuration in UDP for each set, or for each frame size in the entire set. So if you want to generate the entire set out, you just say at the bottom, look at the examples, genconfig-G, which is going to say your generation type. I want to generate the RFC 2544 frame set. I want to use a source IP address of 1.10, a destination IP address of 20, and a destination port of 123, so NTP in this example. It's going to generate the entire set, so you have the 64-byte, 128, 256, so on and so forth, with those values, so that you can just take trafgen, say read it in, send out your interface to those machines, hit your machine, and you can test it that way. So it makes testing simple. Because it's a pain making your own configurations from scratch. Another example was I did a beacon frame generator. So this one we use raw 802.11. It is a frame that says you can actually specify up to 8 characters the SSID value. You can tell trafgen to generate a frame with SSID of 8 bytes. And I use the example of free Wi-Fi here. And you pipe into trafgen, and you'll have that. So you can, if you want to do send a lot of frames very quickly, you could do that. And that, well, I imagine Aircrack NG won't be able to touch this. So it's something you can try. So anyways, next one. So performance test. What can we do? Well, here's an example of how you can conduct a performance test. So we want to create the packet distributions in the RFC 2544 document. And there's the sizes. We could then send those sizes to a destination machine. You want to directly connect them. So that takes out any middleman, like a switch, that may drop packets too. So you have the performance from here through the cable to the destination machine. That's the best way to do performance testing, because it takes out any problems with middleman devices. And then on the receiving machine, I would first verify as I'm generating traffic to see what the performance level is. I use IFPPS, which is included in the netsniff NG suite. And we'll talk about that. And that just gives you some byte counts, some performance counts, some system metrics, CPU time, and so on and so forth. IRQ settings or values. And then what I would do is, if you can script all this, if you want to do packet capture tests, and this is what this example is for, you want to test TCP dump versus gulp versus netsniff NG versus daemon logger versus time machine, and so on and so forth, versus, I mentioned dump cap and T-Shark. So what we do is, we would maybe take a script and have it, have this tool, TCP dump, run 10 times on the destination machine. Trafgen sends that traffic, say 15 million frames. You script it so that it kills it after those frames are sent, so you can give it a gap of 15 million frames, 64-byte packets would not take very long. It's probably less than a minute. At least it was on my machine, I think. So you can kill it after 2 minutes to give it a gap, and then rerun another process. You can do this for all the tools, and then have them write to a file, and at the end you can use a tool like capinfos to read how many packets were written to disk versus how many trafgen sent. You sent 15 million, and you only captured 13 million, you lost 2 million packets. So you can do it kind of like that. And you would want to test not just disk, but you want to write to memory, because disk is very slow unless you have high-performance disk or a large array RAID or something like that. Or you can write to dev null too, if you don't want to capture the writing mechanisms in the code, in most of the code, and get the disk out of the way, just write to dev null. And then at the end, you can use an awk script. I'm working on kind of this whole thing right now, so in the future I'll have it done. It's a lot of work, I tell you. But you can use awk to read the values from and then calculate, do some math, and average packet loss, the number divided by how many there are, and so on and so forth. Okay, so here's an example of full content daily PCAPs, where we have 3 NICs in the system, and we want to send, say we have a span port in our switches, we want to send to this interface, to this interface, and to this interface. We run 3 instances of netsniff NG, and we want to use a timestamp format. And this example is just pretty much here to show you how many options you get with netsniff NG. This uses a lot of them. So we want to drop a privilege level. We don't want our netsniff NG to run as root in case there's a issue or vulnerability with the BPF filter in the kernel, or the application itself, or even the dissectors in the application. So that's good practice. We specify the ring sizes and so on and so forth. Hardware considerations. So if you're doing a high-performance packet data or packet capture, there's a lot of things to consider. It's really almost overwhelming. And here are a few. So first of all, we want NAPI drivers. So in the Linux kernel, NAPI is the new application programming interface. So driver code was rewritten at a point after 2 something in the kernel, where it's more efficient. Basically, the NAPI drivers now have built-in interrupt throttling and mechanisms, so you're not generating 70,000 interrupts starving your CPU from all the other processes except the capturing process. You know what I mean? Because every time packet comes in, it used to be a hit and made an interrupt. So if you have 70,000 packets come in, estimation 70,000 interrupts, CPUs interrupt every single time, that's a problem. So we also have RSS, receive side scaling. This is a mechanism to distribute load from the network card into multiple CPU queues. RPS, this is the software implementation of receive side scaling called receive packet steering, and that is if you do not have a NIC card that is capable of multi-queuing, then you can do it in the Linux kernel by actually, there's a mechanism, it used to be that packets were buffered in the backlog queue. And in this case, we actually don't use that, really don't use it anymore. And if you implement RPS, it actually buffers those packets across the CPUs in each CPU's backlog queue. So you can do that if you don't have a NIC that can support doesn't support multi-queues. So many modern NICs that are in, $400 plus range and up is usually support RSS. But if you don't have that, you're on some commodities hardware, then you may want to look at RPS. Queue length is how many packets you can fit in a queue before they start falling off, the buffer overflows. Offloading mechanisms, so you want to, if you can, and your NIC can perform it, you want to offload checksumming, you want to do UDP segmentation offloading, TCP segmentation offloading if your NIC can handle it, because that takes load off your CPU. A few other things, obviously you want a large amount of RAM, multi-core CPUs, you want to take advantage of hardware locality if you can. If you have use DMA, many cards now, modern ones will use DMA, direct memory access. Direct cache access, that's like an Intel thing. We can take advantage of caches to take in packets. And if you don't have fast disk, write to a temporary RAM-based file system. Or buffer into memory into as much as you can, and then write to disk later. PCIe bus is pretty much what you need. You don't want anything lower if you're doing high performance stuff. And here's some more software configurations or considerations. So use the latest mainline or stable Linux kernel. And that is because if you're using a tool like netsniff NG anyway, you'll have the latest features and you can take advantage of those. And a lot of those, the latest kernels have latest fixes, latest features, latest bug, bug fixes, I guess you could say. And what we'll need to do is tune. So after you have latest kernel, or a recent one, what you want to do is you want to tune your system. And that is trying to test, you would use TrackGen, for example, and just test a number of values, try to find what's optimal for your system. What is optimal for one system may not be optimal for another system. And you'll probably find that is the case all the way around. So here is an example of increasing the socket buffers with rm_max, increase the value. The TXQ length, we increase the, that is the QDIS length in the system. So packets go into queues from the driver into, or actually if it's transmitting into the queues, then to the driver, and so on. But we increase like the queue to 10,000, defaults in many cars to 1,000 packets. We want to say SMP or IRQ affinity. If we can bind a specific interrupt to a specific CPU and take advantage of that. See, there's a CPU that isn't like CPU 0 is usually used for a lot of the operating system stuff. So if you can use CPU 8 for your traffic generation stuff and then use the IRQ for that NIC and set a affinity to that, then that CPU 8 or 10 or whatever it is will take advantage of that and handle all those interrupts and give away to the CPU 0. So we can back off a bit. We can set the value of the JIT compiler. I told you earlier that netsniff ng automatically does that. This is how you would do it. If you want to do it right now on your laptops, you would just do this value, echo 1 into that value in the procfs. And if you want to do the RAM-based file system, then you can use a command like this. This creates a 24 gigabyte temporary RAM-based file system. If you have the memory, you can do that. I mount it to RAM disk, and you can write to that. Okay, let's get on the next tool. So BPFC, this is a Berkeley packet filter compiler. And it supports the Linux kernel extension. This is very cool because Linux has a bunch of extensions that are really not documented. You can't really find them anywhere unless you read some of the code. And they're defined in filter.h, I believe. I don't know if I have that in my footnotes here. No, I don't. No, that one. But anyways, I think it's filter.h. And if you look in the Linux source tree, there's a bunch of them. And we can take advantage of this. libpcap does not support many of these filters. So we can do things that we couldn't do with the normal BPF. One example is you can filter on CPU. You can filter on your RX hash if you have an RSS system using receive size scaling. Hashes are used to distribute packets based on some tuples. You can actually use the RX hash if you know the value. You could probably, I don't know, but you might be able to get it from ethtool or even set it by ethtool for some of the cards. And you can actually filter on that. You can filter on VLANs. You can filter on all kinds of things, which is really nice. So you don't get this kind of granular configurability with libpcap. So we can also use, this is something interesting. I didn't know this. So there's actually security compilation BPF filters. Google Chrome uses this. I just found out this recently. So you can actually use BPF filters to filter on system calls. Have an application. You don't want, some bad system call that could be bad, that has vulnerable, blah, blah, blah. You can actually filter that. And Google Chrome on Linux, of course, only because I think sec filters are only for Linux. And OpenSSH does this. The SSHD daemon, that will actually use some of those Linux BPF filters to filter out calls, which is really nice. So you can actually write those calls, or you can write those filters from BPFC, which is really cool. Another thing is, I found out recently that IP tables, you can actually tell IP tables to read in a BPF file. And now BPFC, you can use a BPFC to create the file and have IP tables write it. So, or use it. IP tables use it and then do the things, whatever it does, to filter on the traffic. So here's an example. I have a file called BPFC ARP. Take it back. I have a file called ARP. I'm going to compile that with BPFC, output to a file called arp.bpf. I then take netsniff and say, hey, read in file with the -f, arp.bpf. The BPF filter is then applied to the socket of netsniff ng, and then you're filtering by the kernel. So what is this used for? Well, for one, pedagogy, teaching. If you want to learn or get good at doing BPF, write it in assembler-like language. That's the way to do it. So also BPF debugging and JIT debugging. So these tools, I should mention again, since they're written by kernel developers, that is their primary concern, is using them for debugging and development. So these aid them in these kind of tasks. And well, I guess I mentioned the bottom one right is to use it to learn to read, write, and debug. So here's some of the extensions I mentioned. The Linux kernel supports these extensions, so you can take advantage of them. And actually, I do have that right. I do have the footnote for this at the bottom. Filter.h. This is in the Linux kernel source tree. If you read this file, these are defined in there. So these are extra extensions that are not documented that you can use via BPFC. So we have packet length, prototype, POFF, which is the one I mentioned in the beginning. That new one that truncates the payload, just writes the headers. The interface index, netlink attributes, mark queue. You can packet queue. You can write CPUs, RX hash, filter, all that. It's pretty cool stuff. So here's an example of a high-level BPF filter using BPFC. So we create a file. This is a text file, right? So we say load at the 8th byte offset of the frame, and this is the source address. So I want to break from that real quick. At the top, we see the libpcap equivalent. So this is how you would do it in libpcap. You want to filter on the source address. I want to filter on the Ethernet MAC address, AABB, CCDD, EEFF. That's what I would do. This is what you would do in netsniff or in BPFC. You would load the value at the 8th byte offset. This is loading a word, 4 bytes. What actually we do That will give us C, C, D, D, E, E, F, F. So in the next instruction, we say jump if not equal those values. It'll go to the next line. If it's not equal, it goes to the drop. There's a label, their drop. So then at the very bottom, if you look at the bottom of the example, drop, it says return 0. So that means return nothing. That is, do not capture the packet. Just, it's gone. So if it does equal C, C, D, D, E, E, F, F, then we load a half word, 2 bytes, at byte offset 6, which is the other AABB part of the frame, source MAC. And then if that does not equal AABB, then we go to drop. If it does equal, we go to the next instruction. And the next instruction is return 1514. So that is return a frame's size of 1514. That can be whatever you want. So like in TCP, you have the snap length. -S, you want to write 96 bytes. You can use that. This is the equivalent. So you just say return X number of bytes. You can use -0 if you want to return the full thing no matter what. That counts jumbo frames. So if you have larger frames than 1514, -0 will count whatever it can have, whatever it has in the buffer. It will turn it loose to you and write that. And this is what happens after you compile it. So it becomes assembler like opcodes, or well, actually instructions. So what we do is, well, actually, let me go ahead. I got to get ahead of myself. So this is an example of using one of those new kernel extensions. So what we got? We have this one that I filter on CPU. An example of this is receive size scaling, or excuse me, receive packet steering. Where in Linux kernel, the packets come in on the NIC. They are distributed among different CPUs, queues, the actual backlogs on the CPU. 10 packets go here, 10 packets go here, 10 packets go here to distribute the load. So one CPU is not handling it all. This is one way you can actually filter for you. I want to grab all the packets on CPU 0, which is pretty cool. So this is how you can do it. Load the value at CPU. So whatever that turns into some instruction. So that's behind the scenes that gets translated to some instruction by the Lex parser. And we say jump if not equal CPU 0. So basically what we're saying is our jump if equal CPU 0. So if it's CPU 0, jump to L1. Which is return, I have -1. And that is return the entire thing. I think it's the same as -0. And then, yeah, that's right. And then L2, if it is not equal, that is jump, if it is equal or not equal to CPU 0, then go to L2. Go to the L2 label, that is return 0, that is return nothing. Which is pretty cool. So this is how we compile it. Pipe it out to a new file called cpu.bpf, tell diffng to read it in. So some notable examples. So a few things that were actually used from this toolkit in the kernel world is TraftJam was used to find and then produce a bug fix for a UDP fragmentation denial of service attack. You can read about it here. This stuff is very technical. So once it was tested, he created a TraftJam configuration of the data that would cause the fragmentation and cause the load on the kernel. And that was able to reproduce it. And once they were able to reproduce it, they created a patch to fix that in the kernel. BPFC was then used to fix a bug in the just-in-time compiler. So Marcus Cotter is a kernel dev, and he wrote one where they found an off-by-1 bug using BPFC in the JIT compiler. So if you want more information about that, just follow the links. So these are real-world examples of netsniff being used in high-profile cases. At least I would call them anything in the kernel I call high-profile, but that's just me. So, all right. So IFPPS. So IFPPS is a tool that just reads in traffic stats. And what it does is read from procfs. So your proc file system, the Linux kernel stores all its stats, right? All the information, all your network card setting, kernel settings, socket settings, all that stuff. It's good. It's there. An example is if you want to read from procfs, you can just command right here. So this would actually read your procnet dev file, which is where your NIC or where the network stack stores network information. This is your packet incoming count, their RX count, TX count, drop count, so on and so forth. And then we can pipe it out to column-T to make it tab separated columns, make it look nice. So why did I give that example? Well, what IFPPS does, it actually reads from procfs, where a lot of the other tools don't. So anything based on libpcap, like iptraf or tcbstat, for example, they use libpcap. And because they use libpcap, and libpcap is at a higher level, it's a library at a higher level, that introduces more processing time. So the results generally will not be the same as reading directly from the kernel. And if you can read from the kernel directly, why not? If the kernel provides the facilities to read from it, why not use them, right? So, an example, one of our developers did a test with iptraf, which is a common packet analysis tool. He does stats, flows. In his system, he generated a bunch of traffic. iptraf, which is libpcap, reported 246,000 packets per second coming in. What the system saw by reading directly from the kernel statistics was 1,378,000 packets per second. That is pretty much line rate. Line rate's 1.4. Yes. That's correct. So what this shows is that at a higher level, this introduces some more latency and more code, right? So if we can get it directly from the kernel, our statistics will be more accurate. Now that is to say, I will make a notion here that for TCP stat, since the kernel does not provide, like NetDev does not provide TCP, like this many packets for UDP, this many packets for TCP, you can't do that from there. So if you want to get that kind of information, that kind of data, then you would use TCP stat, which actually can apply the filters and filter on those values. You know, I want this number. Count me how many TCP segments are coming in right here. You know, we can't do that with this lower level stuff because we're reading from the network card values, the kernel values for this stuff. So we can also use IFPPS to replace VMstat and other IFstat and other tools if you need to. Actually, I like it. Instead of having, usually I would have two windows open. I would use VMstat to get system information, interrupts, context switches, kernel load, all that stuff, and then have IFPPS in another window. But with, or not IFPPS, I have whatever other tool I was using to read from procnetdev. I wrote a script to do it too. So, but anyways, you can just use IFPPS, which actually includes pretty much all those values in VMstat and your network statistics. You get in one window. It's just kind of nice. So if you want to do network stuff and you want to see the load at the same time, you can use IFPPS or IFPPS. So it's pretty cool. And a new feature that was recently added is -P, capital P, that actually shows you the percentage of line rate of traffic hitting your network card. And what it does is it actually goes, reads from the proc file system. It finds out what the speed of your NIC is by reading from the class files. So it say, you know, there's like sys, class, net, Ethernet, and they're about 8012, how many are Ethernet cards, and then there's an actual file in there that specifies the speed. It's called speed. And you read from that, and it gives you the speed. So if you're gigabit internet, it'd be 1,000. If you're 10 gigabits per second, it'd be 10,000. So you read from that, and then you do the math from the number of coming in per second to show you a percentage of the traffic hitting your machine, which is pretty cool. And that's how I got those values earlier, as you saw in my traffic gen test, where I said, you know, 64 packets, I got, you know, whatever percentage I had on there, or 15, 14 bytes per all the frames that are at bytes 15, 14, I was hit 98%. That's where I got those percentages from. And we can also pipe the GNU plot. Use comma or CSV, but actually it is white space delimited format. So you can output to a file, and then you can read them in. So here's an example of IFPPS in a virtual machine. So I don't have many CPU. This machine's not really doing anything. 360 packets per second. So I didn't have a really good example of all the stuff. But this is basically what it looks like. So you have the CPUs listed. So for every CPU, will have a new column or new line all the way down. You get the drops, the translation from bits to bytes, megabytes, blah, blah, blah on there. Errors, CPU, context switches, interrupts, all that. So here's an example of the CSV. So if you write to CSV using the -C option, what we can do is write to a file and then parse it in some way. I use awk because I like awk. Awk is awesome. So this is an example. I say awk. We're going to skip the header, so any line that matches a regular expression, caret, pound, skip the header. And then what we want to do is print the third column and put packets per second and then the third column from the ifpps.csv file, and I print the top three because there's a lot. And this just gives you the packets per second for every interval. And by default, PPF or if PPS uses a 1 second interval, but you can change it whatever you want. So for every second, this is how many packets are coming into my system. You can do the same, and you can do a time conversion because Gawk actually has a string to time function. Awk does not, so you have to use Gawk. And you can actually take that, the timestamp is in Unix epoch format, right? It's that ugly number that nobody likes. So what we do is we convert that with the string function, and then we say, I want to find at every time interval in the drop column a value greater than 0. That means we drop some amount of packets that were not 0. And I want to find in the error column, my network card, any number of errors, and then it returns it. So here, I found that at this particular time of the day, I dropped 900 packets, 100, and there were 3 errors. And with this, because it is white space separated, even though it says CSV, we can use GNU plot to read it. So here's an example of using GNU plot. So we just graphed a run I did, and we're about 650,000 packets per second, hitting an interface. And at the bottom is the drop count, the little red line. Again, we actually key in on what I just did, and you can see, just by reading those drop values, we key in on it, and we can just see, hey, we're about a little less than 40,000 packets at certain intervals. Well, we're dropped there. So whatever the interval was, we see some loss. We can key on those specific values. FlowTop. FlowTop is the next tool. This is a pretty cool tool. So FlowTop is a connection tracker. And what's neat about Flowtrop is it hooks into IP tables, or actually the net filter code. So to run it, you would enable IP tables. And if you want actually Flowtrop to be able to access all the value or all the traffic, you say, IP tables -j allow for everything, allow all UDP, TCP, whatever. So with that, anything that is allowed to pass through the IP tables code, the net filter code, well then Flowtrop will pick up. And it does GeoIP location, as you can see. Process ID is for the process that will receive the packet, which is really cool. Then the name. So in this example, I did a test where I used wget to make a web request to, I imagine it was Google. And let's look at that FTP up there too. So anyways, I made a request, and it shows you the TCP states. I got established, time, wait, so on and so forth. The wget process, the IP version 4, IP6, whether it was that, and then the GeoIP location for each one. So this is cool for incident response. If you're on a machine that's owned and you want to see what processes are coming, or what packets are coming to what processes, you could use this. All right, so we're wrapping it up here. So at the end, we have an example of installation. So this is generally how you could do install netsniff ng on an Ubuntu-like system. Ubuntu's and Debian are a particularly popular system, so this is an example. So basically, you should be able to copy and paste this. There may have been some changes. If not, I have in my references, I documented some stuff. I did some installation docs for this. So you can find those, or you can email me if you need help, or the list. So anyway, so just install all those packages, clone the netsniff ng from the repository, compile it, and you have it. So a few things in the future. What could be next? Well, there's some really interesting things going on. First, more dissectors. There's talk about a netlink dissector. So if you're dissecting the kernel to user space messages that pass for process communication, there's going to be one of those in the future. Compressed on-the-fly bitmax indexing is something that a lot of people are looking forward to. So I hope that comes out sometime soon. And this allows you to search through large PCAPs much quicker. Another thing is the packet fanout. The Linux kernel has this new thing called the packet fanout. And that is you can distribute packets among multiple sockets. So this is kind of like what pfring does in a sense, except pfring is not native, right? It's not included in the Linux kernel source tree. It's a third-party module. And I like pfring. It's really cool. But now the Linux kernel provides facilities to take advantage of this. So netsniff ng, or the developers, they're thinking about finding a way to do multi-threaded packet fanout. So we can take in packets and distribute them in multiple sockets so that one does not become overwhelmed and have them all writing to disk or whatever. This will be probably really nice for 10 gigabit per second situations and up probably. So, and then another thing is optimize performance. So hacking on AF_packet. So hacking on the kernel packet facilities to find out ways to optimize. That's something I'm excited about in the future. And performance benchmarks on 10 gigabits per second on modern machines. Some beefy machines would be really nice to see what it can do. So there's a few other things up there. You don't need to go through all of them. Here's my notes. So a few documents I've written. If you want to find configuration files, you may be able to use those Google Dork at the bottom I came up with to maybe find some BPF files or traffic configuration people have out in their directories on their web interfaces or whatever. So. And I have a detailed TraftGen expression language article, so if you want to see a lot of the nuances of TraftGen expressions, go to that link. Right. Any questions? All right. Well, hey, no questions. That's all right. I'm not going to say more than I pass packets, but yes, I do. There was a lot to cover in this presentation. So. Well, I appreciate it, guys. If you have any questions, feel free to email me or email the list, the Google Groups mailing list. The guys there's always someone ready to respond. And I guess that'd be all. You can come talk to me. Thank you, guys. Appreciate it.